Hello, my name is Drew Fustini, and I'd like to talk about the future of Linux on RISC-V. And there's many links in these slides, so you can find them at that URL at the top there, tinyurl.com/rv/linux/dus. So who am I? I design open source hardware projects for a PCB manufacturing service in the US named OshPark. I'm also on the board of directors of the Beagle Border Dog Foundation. You might be familiar with the BeagleBone. It's a small open source hardware Linux computer. I'm also on the board of directors of the Open Source Hardware Association, and we have an open source hardware certification program that you can find out more about on our website. And I'm also an ambassador for RISC-V International. So this is one of the great RISC-V meetups from around the world, and there's other ones in many other time zones, and you can find them all at community.riscv.org. And coming up in July is the RISC-V Forum for Embedded Technology. So sometimes when I give this talk, I go a lot into the basics of RISC-V, and since this is already a RISC-V meetup, I'm only going to focus on the parts that are kind of important for Linux. So with RISC-V, we have 4 base integer ISAs, and RV64 is the 64-bit one, and this is going to be most interesting for Linux. We also have standard extensions, and for Linux distros like Debian and Fedora, they're targeting RV64GC. So that G stands for general purpose, and it's equivalent to integer, multiply, atomic, float, and double float, along with C for compressed instructions similar to ARM thumb. If you want to learn more about RISC-V, I highly recommend the RISC-V Reader. It's only about 100 pages. You can find it. It's available in several different languages, and it's available, and you can find out more at risc5book.com. So sometimes I get the question, is RISC-V an open source processor? And RISC-V itself is just a set of specifications under an open source license. And RISC-V implementations can be either open source or proprietary. But open specifications make open source implementations possible. So an open ISA like RISC-V enables open source processor implementations, which is something I'm really excited about. So in terms of what Linux needs from a RISC-V system to run, an important part is the privileged architecture specification. So this provides 3 different privilege modes. At the bottom we have machine mode or M mode, where our bootloader and firmware would run. And then we have supervisor mode or S mode, where the operating system such as the Linux kernel would run. And then we have user mode or U mode, where the applications would run. And then there's several different combinations that can be used. So a simple bare metal embedded system would just be M. An embedded system with memory protection would be M plus U. And then a full Unix style operating system like Linux with virtual memory would be M plus S plus U. So the RISC-V boot flow might look similar to what you find on an ARM SoC. We have a boot ROM, first stage bootloader, and then U-boot that loads and jumps to the Linux kernel. But we have something new in the middle there for RISC-V, and that's SBI. So SBI stands for the Supervisor Binary Interface. So this allows supervisor mode software like the Linux kernel to be portable across all RISC-V implementations by defining an abstraction for platform-specific functionality. So the supervisor execution environment, or SEE, handles SBI calls from the kernel and is implemented by firmware executing in machine mode. So you can see here on this diagram we have the kernel running in S mode, and it makes SBI calls down to M mode. So SBI is required by the Unix class platform specification, and soon this will be replaced by the RISC-V platform specification. I'll talk more about that at the end. If you want to look at the discussion for both of these, it's on the Tech Unix platform spec mailing list. So in SBI we have several extensions. So starting off with the base extension, which basically allows us to query what version is it, which implementation is it, along with things like the machine vendor, architecture, and implementation. And then we also have the timer extension, the IPI extension for interprocessor interrupts, and the remote fence extension. So OpenSBI is an open source implementation for the SBI spec. And the idea here is to avoid fragmentation by having layers of implementation. So we start off with a core platform-independent SBI library that firmware or bootloaders can link against, and then also it can integrate with platform-specific operations provided by firmware. It also is runtime firmware for supported platforms. And it replaces, you may see this in other places, the legacy RISC-V PK bootloader, which is also known as BBL for Berkeley bootloader. So that's the old thing before OpenSBI existed. And then OpenSBI allows us to use well-known bootloaders such as U-Boot. And there's now a trend in OpenSBI to move away from having a new platform added for every new SoC and just use something called generic platform. So SBI also works with the hypervisor extension, which is currently in draft. So we have an additional thing called the HS mode. So we'll have the guest kernel making SBI calls to the hypervisor in HS mode, and then that'll be making SBI calls down to the machine mode or M mode. So SBI does have continuing releases. So the current release candidate is for version 0.03. And this adds the suspend functionality is added to the heart state management, which there's a little chart on the side here of how that works. There's also the performance monitoring unit function that was added and the system reset extension that was added so that you can fully reboot the system. So if you're not familiar with the term heart, it's a term used in RISC-V to mean a hardware execution context. So this contains all the state mandated by the ISA, so the program counter and certain registers. So for example, you can think of an Intel CPU with 2 cores with hyperthreading on each. That would essentially be 4 hearts. So if we have a RISC-V processor with 4 hearts, you could kind of think of it as 4 cores in a system that didn't have hyperthreading. Or in the context of Linux, if we have 4 hearts, we would have 4 schedulable processors, or we'd have four penguins when our system boots up. So RISC-V also supports UEFI now. So support was added into the Linux kernel in 5.10. U-Boot and Tiano Core EDK2 both have UEFI implementations, and Grub2 can be used as a UEFI payload. So there is full support for RISC-V and QEMU from both 32-bit and 64-bit, and you can pretty much do all the different draft specifications in it for hypervisor and vector. You can run OpenSBI, U-Boot, and Core Boot. You can even run the same binaries that you would on a physical board. And there's a nice tutorial from Michael Optenhacker at FOSDEM 2021 that talks about how to build an embedded Linux system from scratch in 45 minutes using QEMU. So RISC-V support was added to the Linux kernel by Palmer Dablet back in Linux 4.15, which was several years ago. There's the Linux-RISC-V mailing list, which is the main place to see patches and discussions about the RISC-V support in the Linux kernel. And there's the archive on lower.kernel.org that you can go back and read all the past discussions of. So last year, Bjorn Topol gave an interesting talk at the Munich RISC-V meetup about what's missing in RISC-V Linux and how you can help. And he made the point that the RISC-V architecture supported Linux is still relatively new compared to other architectures. So it's a great way to jump in and learn the nitty-gritty details of the Linux kernel. And also because it's a relatively newer architecture, it's still a pretty small community, so it's a great time to get involved with one of the architecture communities in Linux. So if you run this shell script in Linux kernel source, it'll show you for each architecture the to-do list. So these are the current to-do items that still need to be done for the architecture support for RISC-V in the Linux kernel. So hopefully that might pique your interest to potentially get involved. Another thing to keep an eye on is there's continual work being done to add new features and functionality, and a lot of that is the way to keep track of that is from the mailing list there. So I highly recommend subscribing to the Linux-RISC-V mailing list if you want to keep up with what's going on with the Linux kernel development for RISC-V, and to just talk about some of the work that's been done over maybe the last year or so for debug, trace, and security. So there's now support for the eBPF JIT for both 64-bit and 32-bit. So we know that eBPF is something we've seen a lot of new interesting applications for beyond just networking in the Linux kernel. And there's also now support for kprobes and kbrep probes, which will allow BPF trace to be used on RISC-V. There's also JUP label support, which reduced overhead of debug and trace features. KGDB and KDB sorts also being worked on. KExec and KDump support as well. There's also work being done on a 64-bit relocatable kernel, which will help kernel address layout randomization for security be implemented in the future. Also, support for the syscaller fuzzer was added, and that's been helping to discover bugs in the kernel code for RISC-V. And also the K-fence, which is the kernel-elentric fence, which is a memory safety error detector, supports being added for RISC-V as well. And each of these links here takes you to the mailing list thread, so if you want to find out more, you can click on the link in the slides and read the mailing list threads about these patches. So in terms of hardware support, KVM support is essentially waiting on ratification of the hypervisor spec. There's also initial support being added for the vector ISA, which is another spec that's in draft. There's also support for SV48, which is 4-level page table implementation, which would allow up to 64 terabytes of physical memory. And like bigger systems like Intel, there's also NUMA support that's being worked on as well for RISC-V. As well for smaller systems, execute in place or XIP support, which allows us to run directly out of flash and reduce RAM usage. More recently, there's been CPU idle support added, which takes advantage of the that hard state management functionality in SPI. And also support being added for some of the SoCs that have been coming out from Kendrite and Microchip and Sci5. So we do have support for RISC-V from Fedora, and the goal of the RISC-V Fedora project is to provide the full Fedora experience on RISC-V. And this has been in the works for several years now, starting off with QEMU, and now it actually runs on real hardware. So you can actually go and grab, at that installation instructions link there, you can go grab a Fedora image right now and run it in QEMU on your system. But it also supports several of the RISC-V development boards that currently exist and will be coming out. Debian also has a port for RISC-V architecture. And Debian is known for their massive collection of packages, and right now 95% of those packages are being built for RISC-V. So if you don't need a full binary distribution like Fedora or Debian, there's also work being done for RISC-V in Open Embedded in Yocto, and that's provided through the Meta RISC-V layer, which is essentially kind of a BSP layer for RISC-V, and that supports both QEMU and some real boards that have come out and ones that will be coming out in the future. And another way to build a kind of your own Linux distribution, your own root file system, if you don't want a full binary distribution, is Buildroot as well, and that has full support for RISC-V in the upstream project. And as I mentioned earlier, there was a great presentation from Michael at Bootland about how to build an embedded Linux system from scratch in 45 minutes. And this is just using QEMU as the hardware, so you don't actually need any real hardware to go through this and build a full RISC-V Linux system from scratch. So some of you may recall a few years ago, Sci5 came out with the Freedom Unleashed board, which is the first Linux-capable RISC-V dev board. And it used a SoC from Sci5 called the Fu740, And this was a lot faster than what people have been using previously, which was FPGA soft cores, which are just inherently slow compared to a real SoC. And one thing to note is oftentimes people say ASIC when they're talking about a real hardcore in a SoC instead of a soft core in an FPGA. But this board was $1,000, and it's no longer available. And the chip on it was never sold separately. And this is because Sci-Fi's core business is designing and licensing cores and not building SoCs or boards themselves. But the neat thing about the Unleashed board was it showed us that we can actually run a full Linux desktop on RISC-V, which was pretty neat to see. So this is a Fedora GNOME image running on the Unleashed with a graphics card plugged into it. So Microchip has the PolarFire SoC. So this is similar to the Sci-Fi U540, but it adds a FPGA. So we have 4 U54 cores from Sci-Fi along with the FPGA fabric, which can potentially make for some pretty interesting systems. And the other thing that's nice about this part is it's intended for full commercial availability. So the part itself is available from distributors, so you can build your own boards with the PolarFire SoC. And Microchip produced the Icicle board as kind of the reference dev kit. Now this is half the price of the Unleashed, and it is available from distributors. So this has 2 gigabytes of memory on it and a built-in eMMC flash. But due to the fact that it has a large FPGA integrated into the SoC, it does kind of have a higher price tag than what some people may want for a dev board. Now to go down to the really low end cost, we have the Kendra K210, which is a 400 megahertz dual core RISC-V system. And you can get a dev board for as cheap as $13. And full support was added into Linux 5.8 by Damien Lamal and Christoph Helvig for this part. And it also has support in U-Boot from Sean Anderson. Now, one of the limitations of this board is it only has 8 megabytes of SRAM. So you can use buildroot to make a rootfs with BusyBox, and there's a nice tutorial on CNX software of how to do that. And Damien Lamal, who helped port Linux to it, has an interesting robot arm project that he used this board with. But with the 8 megabytes of SRAM, it runs out really fast. And the MMU in the system is based on a draft spec that's not supported by Linux. So we don't have virtual memory, which means we can't use like shared libraries like we normally would. So it's pretty limited in terms of the memory. But for $13, it's a really nice way to play around with some real RISC-V hardware that can run Linux. Now, last year, Sci-Fi announced the follow-up to the Unleashed, which is called the Unmatched. So instead of $1,000, this one's $665, so a little bit cheaper. It was available on CrowdSupply as well, and it's finally shipping now to backers, and then it'll soon be available from distributors as well. So this has a new SoC in it called the Fu740 SoC. So it also has 4 64-bit RISC-V cores, similar to the other one, but just kind of the next generation of Sci-Fi core design. And the really interesting thing about this board is it comes in a mini ITX PC form factor with 8 gigabytes of memory. So, and with USB 3 and gigabit Ethernet, and it even has a PCI Express expansion port along with slots for an NVMe M2 drive or Wi-Fi and Bluetooth. So as shown in this picture here, you can actually have a full development workstation that's running natively on RISC-V, which is pretty neat. So Alibaba has a chip design division called T-Head, and they've designed a really high-end 16-core 2.5 gigahertz RISC-V processor. It also implements the draft of the Vector extension, which is, I think, will be a really interesting way in which people will be able to do certain types of programming much better with the RISC-V than with alternatives. It's comparable in performance to an ARM Cortex A73, so much kind of higher end than the previous cores that we were looking at. There's an interesting paper last year from Hot Chips that talks about the design of the system and how they're currently using it in an FPGA implementation in some of the Alibaba data centers. And Alibaba T had actually produced a test SoC called the C910, and they ported Android to it. So really neat thing that we have a RISC-V SoC with Android running on it now. And you can find out more information at that link there about the project. There's now actually an Android special interest group from RISC-V International with people from Alibaba and other organizations that are working on getting Android support better in RISC-V. So the EVIL board that you saw there is called the T-Head ICE evaluation board. So this is that C910 test SoC. So this has that 910 core, 2 of them, and then actually I think 3 of them actually, along with DDR4 and gigabit Ethernet and a GPU. Now this isn't, the board and the SoC are not available for sale now, but this was a really awesome proof of concept, and we'll see where Alibaba T-Head goes from there with this system. And on the lower end, T-Head also has the C906 core. So this is a smaller in-order pipeline that's just 1 gigahertz single core system. And this is being used in the recently announced Allwinner D1 SoC. So this is meant to be a low-cost RISC-V single-core SoC. And they've also produced the Allwinner. So Allwinner Online has created the D1 development board called the NEZA. And this has the 1 gigahertz single-core D1 in it, along with DDR3 memory, Wi-Fi and Ethernet, USB, and several other peripherals as well. And one of the exciting things that was announced, I believe, last month was that RISC-V International is starting a developer board program. So you'll be able to sign up and potentially get a Linux-capable dev board to work on your development projects. So this was starting off with the Allwinner D1 board, but then eventually it'll be including other vendors' boards like the Sci-Fi Unmatched and the Icicle, and the Beagle 5 and some other ones as they come out. The way to get started with this is you go and fill out the RISC-V developer boards form, and the preference is for people to be members of RISC-V International. So one thing to remember is that individuals can actually join free of cost. So if you go to riscv.org, you can actually sign up free of cost as an individual. And when you fill out this form, you need to explain what project you're wanting to work on and why you're interested in RISC-V. So for example, it might be that you want to ask RISC-V support to a certain upstream open source project. So back in January, Beagle.org Foundation, Seed Studio, and Star5 announced the open source hardware Beagle 5 Starlight development board, which features a 64-bit RISC-V SoC from Star5 that, similar to the Icicle, or similar to the Unmatched board, features several U74 Sci5 cores. So the Beagle 5 Starlight board you see here, it has 8 gigabytes of memory, 4 USB 3 ports, 2 CSI ports for camera, DSI for display, HDMI, gigabit Ethernet, and Wi-Fi and Bluetooth. So back in April, we sent a limited number of beta development boards to upstream developers from different open source projects such as Linux kernel and U-Boot and OpenSPI to start kickstarting getting RISC-V support added in. And one of the really neat things was Thomas Petazzoni of Bootland added support to Buildroot for the board in just 48 hours, so that was neat to see. And he also wrote a really nice blog post about how he went through and added support in Buildroot for a new RISC-V SoC and board. And Kemraj also and some others also did a similar thing for the Meta RISC-V layer in Yocto and Open Embedded. And if you want to find out more, please join the public Beagle 5 forum group on our website, and you can find out more about the future product launch of the board. And if you don't have any hardware at all, I would highly recommend Renode. So similar to QEMU, but more tailored towards specific boards, Renode can simulate physical hardware systems, including the CPU, peripherals, sensors, and even wired and wireless networks between nodes. So if you go to the Renode website, you can see they have profiles for different boards, including that Hi5 Unleashed board that I was talking about earlier. So here's me on a train actually going to, I think, Embedded World last year from Berlin, where I was living at the time. So I'm on the Deutschbahn and I'm simulating the Sci5 Unleashed board using Renode on my laptop. And Renode now has support for the Beagle 5 Starlight. So even before the board comes out as a product, you can go and emulate the Beagle 5 Starlight on your laptop or workstation. So one of the things I wanted to go over in the end here is that there's the RISC-V Tech Groups calendar. So there's a large number of different working groups and committee meetings that members can attend. And remember that individual people and nonprofits can become members of RISC-V International free of cost. So if you're interested in some of the things I was talking about, one of the ways that I kind of stay involved and know what's going on is I like to try and attend some of these different working groups and committee meetings, and many of them meet on either monthly or bi-weekly basis. So this is just a snapshot of the current calendar from June. If you click on that link at top there, it'll take you to the Google Calendar where you can see all the different meetings that are going on. And I just wanted to go over some of the ones that are particularly of interest, I think, for people that are looking to do Linux RISC-V systems. And I mentioned back during the SBI section that's a requirement for the Unix platform specification. Now that's kind of being overhauled into a new thing called the RISC-V platform specification. So there's the Platform Horizontal Steering Committee that is working to standardize the interface between hardware platforms and OS like Linux in the context of RISC-V. So if you're interested in this, the agenda and minutes from the bi-weekly meetings are available online. Also, recordings for past meetings are available online as well, and they're really, Kumar, who's the chair, is really good about recording them, since it might be a tough time zone for some people. I have a link in there to the last meeting slides, and the discussion for this happens on the Tech Unix Platform Spec mailing list. So just to give you a brief overview, so this draft platform specification has two different platforms defined. So there's OS-A, which is meant to be used for rich, full operating systems like Linux, and even has an optional server extension to talk about the things that a RISC-V server should have. And then there's the M platform, which is meant for bare metal applications or an RTOS running on a microcontroller. And these are still in development, so if you're interested in this, both in terms of what you need as someone that's looking to use a system, or you want to make sure that you're including the right things in RISC-V systems that you're building, I recommend checking out the past meetings and hopefully attending in the future. And kind of related to this, there's a new special interest group called the Advanced Interrupt Architecture. And this is actually defining some new hardware. So it's not ISA spec, but it's kind of a spec for hardware that complements it. So this includes a new platform level interrupt controller called the APLIC. And then in the context of PCI, we have what's called the message signal interrupt. So this adds the incoming MSI controller as well. There's a draft of the current spec, and then I linked in the slides from the last meeting. And you can follow the discussion on this Tech AIA mailing list. And also related to this, there's also, so we used to have the PLIC, and now that's being replaced with the APLIC. And then there used to be the CLINT for core local interrupter, and there's now the advanced CLINT that kind of replaces that. And it defines a set of memory mapped devices which provide interprocessor interrupts and timer functionalities for each heart on a multi-heart system, so like a multi-core system. There's discussion for that on the Unix platform mailing list. And there's even been a Linux patch posted by a noob to give initial support for the ACLINT. And this is a chart from the last meeting of the AIA that kind of shows the different tiers of platforms, such as existing platforms or ones with wired interrupts, or platforms with MSIs for PCI, and then also wired interrupts, and how these different specifications fit into that picture. Now, I had mentioned the draft of the RISC-V hypervisor earlier, and how there's currently a patch set that adds support for that in KVM, which is the virtual machine that's part of the Linux kernel. And recently, Linux Weekly News, which is one of my favorite websites, had a story about why RISC-V doesn't yet support KVM. And I highly recommend reading this thread here from the Linux kernel mailing list, which was sparked off by a new posting the most recent revision of the patch set. So the gist of it here is that the Linux RISC-V Arch maintainers only want to support frozen specs. But there's been an unexpected delay from the RISC-V International ISA group in getting the hypervisor extension frozen. So we have this tension here between people like Anoop that are carrying this patch set for like over a year plus that want to get it merged in, but then at the same time, the people like Palmer that are the RISC-V Arch maintainers in Linux, they don't really want to start merging in support for a spec that's not frozen yet. So there's not necessarily like a right or wrong answer here, but I highly recommend checking out this discussion if you're interested in that and seeing how hopefully we can find a compromise that balances both of those sort of needs. And this also, outside of the Linux kernel mailing list, has also kind of reawakened discussion on the tech privilege mailing list around the freeze of the H extension or the hypervisor extension. And kind of another similar thing of kind of real-world meeting spec is recently there was a patch post on the Linux kernel mailing list about a vendor, Alibaba T-Had, that had added custom page table attributes to handle peripherals that were not on a cache coherent interconnect. So this was something where we did not actually have any capability in the RISC-V ISA for this, so the vendor had gone off and kind of come up with their best way of trying to add that capability. And now we have that kind of position where we need to figure out how to reconcile both what vendors are doing with real hardware right now and what we want the specification to be. So specifically in this instance, there's an extension that's proposed currently called the Page-Based Memory Types, or PBMT. So this was proposed on the Tech VertMem mailing list. So there's existing PMAs or physical memory attributes in RISC-V, but they're not sufficient for some platforms, such as a SoC that has peripherals on a non-cache coherent interconnect. So PBMT, or as you'll see formally SVPBMT, which is a bit of a mouthful, defines these different page-based attributes, which are more granular than the PMA. So we have just normal memory, normal cacheable region, WB, and then we have NC, which is a non-cacheable region, and then we have UC, which is a non-cacheable IO region, which would be useful for things like DMA descriptors. So the last meeting, I linked in the meeting minutes, and the next one is coming up on June 23rd. So if you're interested in things like this, I'd highly recommend joining. The last meeting was quite interesting. And there's not necessarily a right or wrong answer here, but there's a lot of good discussion around the different trade-offs and trying to find a compromise that works both with what vendors have already done and what's kind of the ideal thing to do for the future. Kind of another thing of like real world versus specification is cache management operations task group. So currently there's no methods in the RISC-V ISA for managing cache and coherency. So the CMO task group has proposed this extension that has a base set of instructions in CSR, which are control and status registers. So this allows essentially management of cache blocks. So you can see some of the instructions there. So this is still in the works, and it probably won't be done anytime soon. So that brings up the question, well, what do we do about existing SoCs? And for the short term, there's been a proposal to add a DMI synchronization extension to SBI. If you remember, the nice thing about SBI is it kind of acts as that abstraction there between the operating system kernel and the specific RISC-V hardware implementation. So we can potentially use that to leverage things like adding a DMI synchronization extension. And then the long term, once this CMO-based extension is approved in the future, we can actually then go back and trap and emulate those new instructions in SBI. So if there's an unknown instruction, that automatically traps into SBI, and then we can handle it in there. So that's another kind of longer term approach for these existing SOCs. So there's the Tech CMO mailing list that has this discussion, and the next meeting is coming up on June 21st. So that's my tour of the future of Linux on RISC-V. And I highly recommend, if you can, try and attend some of these working groups and committees. I'll go back to that slide right here. So the RISC-V Tech Groups calendar. A lot of interesting development and discussion going on, and hopefully there's something for everyone's area of interest. And I'll jump back here to the final slide with that tiny URL link there. That'll take you to the slides here with all the links. So thank you for listening, and happy to take questions, which will be in the meetup and not in this video. Bye.